Hi everyone, my name is Sanjiv. Welcome to our talk on types for quality. We're going to start off with 4 different presentations and end up with some questions at the end. Oh, I just have to move this around. To start us off, we have Luke, who's going to talk to us about some common problems we face when developing software. So over to you, Luke.
Thanks, Sanjiv. So let's for a minute just pretend we're consumers of this API that I've got up here. So it's called def load user, takes an ID. So, the speaker's notes aren't showing. Cool. I'll just use that. Cool. So, as programmers, working with an API like this, it's our bread and butter. We deal with function signatures like this all of the time. So we might have some questions that we want to ask about this API. So this ID parameter, what sort of parameter is it? Is it an int, is it a string, or is it something else? The return type from this method, well, we can infer from the name that it's probably going to return a user, but what exactly is this user object? What happens if the user can't be found? Do we return a null? Do we return a null object? Or do we throw an exception? And what if the user if actually loading the user fails? So we're probably getting this user from a database or across the network, and that can fail. And then finally, even if I think I've understood the answer to all those questions, how do I still go about ensuring that I've correctly consumed the API? Cool. So the answer to those questions. So I might control click and go and read the implementation of that method. Or I might read through the documentation that's been provided by the original author. Or there might be some conventions on that method name. Like it might have a suffix of question mark to convey that it returns a Boolean. Or the parameter might be called int ID. Or finally, I might have a look at the tests to see what the original author had intended. But all of these strategies rely on me as a human kind of interpreting some information that somebody else has provided. And as humans, we're really well known for making mistakes. So they're all kind of very flawed approaches, in my opinion. So documentation and these other things do serve a purpose, but documentation should be there to provide like really interesting and enlightening information about a function, not just the trivial basics like what sort of argument type that it accepts. And then if we switch context and we think that we're now maintaining this method, so all of those questions that I had before still apply. So this ID, what sort of types of values can be supplied to the function? Everywhere this ID is, do I need to validate that it's not supplied an invalid parameter, or do I just assume that it will fall into how it should be provided? As I'm modifying this function, how do I ensure that I don't break existing callers of the function? And finally, if I actually do need to change the contract on this function, how do I go about doing this and ensuring that I don't break existing clients? Well, I will break them, but how do I ensure that I bring them on that journey? So this is where static types are here to help us. So static types help us answer all those questions that I outlined before. And while they provide us interesting information as humans, they remove the human element of mistakes through misinterpretation. So all languages have types. The differences between when those types are checked. So does that occur at build time or compile time, or does it occur at runtime? So static types are verified at build time. So I don't think there's any debate that these sorts of behaviours we want to be checked, at build time. We don't want users seeing, misinterpretations in our code occurring at runtime. So the difference really is between whether or not you want tooling to perform these checks for you, or whether or not you want to write your own tests that exercise these same scenarios. So traditionally we think of static types as being checked by a compiler, for example, Scala or Java. But more recently, there are languages which we consider as traditionally dynamically typed, like JavaScript, Ruby, and Python, now have kind of build time bolt-ons that apply type checking. For example, there's Flow for JavaScript. So that's just a general outline of the problem space. I'm going to hand over to Tim now to further enlighten you.
Thanks, Luke. So basically, as Luke mentioned, you can use your type checker or compiler if you do have a compiler. It's very important to work with your type checker to ensure your API, your function define. Where's my? So it's very important to work with your type checker to kind of supply your type signature. And one simple change we can make here is to make ID a string, so we know it won't be an integer. And what about return type? We can make it a user, so we know it's going to be a user. What about user not found? In some cases, how do you define a user not found? You're probably thinking about you can use a null or you can use a user not found exception. But is there a better option? And how do we communicate this using type signature? So let me introduce you option. So option is a type class that represents that encapsulates an optional value. So option takes a type parameter A, and so it can be a none or it can be some type of A. In this example, we change the function signature to return an option of user. So that means when there's a user form, and then we can return some user. Otherwise, we can just return none. So a program might fail for various of reasons. So how do we model this? How do we communicate this with our function user? So we can change the low user to return either of arrow or user. So what does this mean? So either is another type class that takes two type parameter. So when it's left, E is returned, and when it's right, A is returned. Going back to our example, we can see, so when there's an arrow, we're going to get a left containing an arrow, and when it's right, and we're going to get a user. And by convention, we use left for arrows and right for success. You probably have heard of ADTs. Let me introduce you that. So ADTs stand for algebraic data types. And ADTs are a very useful programming construct that allows you to define a fixed set of values. So option and either are both ADTs. So you are probably using ADTs without even realizing it. And so ADTs, to keep it simple, you can implement custom ADTs by doing subclassing, and you can destruct your ADTs through pattern matching. In this example, first we define our low user function to return either arrow or user. Then when we call the low user, we pattern match on the return value. So when it's a left, a arrow is returned. So we just simply say log arrow. When it's a right, and we just say hello user. And so your type checker or compiler will make sure it covers all possibilities. So there's no room for errors. So hopefully we have defined our function in a better way. I'll hand over to Andrew to talk about how types relate to tests.
So imagine we have the above code to load a user given a user ID. We have user ID as a parameter, and then we connect to the database and fetch user details. Then we transform the user details to get the final user structure. So what's wrong with the above code? Well, what happens if we can't connect to the database? Perhaps the developer forgot to handle that case correctly. Also, maybe the user ID that's supplied to the function is invalid, and the developer forgot to handle that. How could we make sure we don't make these kinds of mistakes in our code? Many dynamic languages will not check even basic things like that the names of the methods we call are correct. So for example, if we look at the code up on the screen, maybe dbfactory.connectToUserDB is actually called connectToUserDB with a lowercase b at the end instead of an uppercase b like we have on the screen. So the usual solution to these types of problems in dynamic languages is to make sure you have as close to 100% test coverage as possible so that you can find those kinds of typos. We could write a test for each specific thing that we need to test. So for example, maybe user DB factory returns null if it can't connect to the database. And we want to make sure that our code is also going to return null in that case. So we'd write a test something like what we see up on the screen to make sure that that behavior actually happens. So tests are therefore a very important quality mechanism when it comes to use when you're programming in dynamically typed languages, to make sure even the most basic aspects of your program are correct. Now, when you're programming in statically typed programming languages, tests are also very important. I'm afraid that types can't completely replace the need for all tests. However, types are an alternative quality mechanism that coexists with tests, and you can use types to ensure that your code is correct. So using the right tool for each job, and sometimes that's tests and sometimes that's types, for a particular task can make your life a lot easier. So tests show that your code is correct for some possible inputs. A good analogy is the exams that you did at university. They covered some of the things that you learned how to do, but it was never possible for the lecturer to ask about every single thing in the exam. So tests in your code are the same. It's easier to verify more complex things using tests rather than types because they don't cover every case. The caveat with tests is that if you don't think about certain corner cases when you write your tests, you might not find a bug until it happens in production. Types, on the other hand, are about proving that something holds for all possible inputs. So for example, that when you add two numbers, you always get a number as the output if you are testing an addition function. So the type checker will ensure that there's no possible inputs allowed by the types for which the output types won't hold. In other words, there's no corner cases with regard to that one thing. In other words, type checking is comprehensive, but tests are not comprehensive. On the other hand, checking the actual numbers that addition produces is much easier with tests compared to with types. For that reason, a good principle to live by is that if you can easily use types to achieve something, use them, but otherwise, write tests. So for example, when calculating the average of a list of numbers, you could use a non-empty list instead of a list, representing that your list can't be empty, eliminating the scenario of accidentally dividing by 0 when you calculate an average. So what this means in practice is that programmers in statically typed languages tend to use types to handle quality for some of the tedious, simple aspects of the program, and use tests to test more complicated business logic. Now let's look at some more concrete examples of how types can cut down on the tests that we need to write. So notice the use of either, as Tim talked about earlier, to represent the possibility of our basic operations up on that code on the screen failing. If we forget to handle the error case, our code won't compile at all, so we don't need to write tests to cover that case. If we consistently use either instead of exceptions, we don't ever need to worry about our program crashing out with an exception. The compiler will tell us if we forget to handle an error. For this reason, we could reduce the number of tests that we need to write. Having types has let us focus on writing tests for the business rules that we really care about. One thing to note about the above code is that we've gone to some extra effort to ensure that different things have different types. We've made a type called user ID to represent our user IDs. Our user ID might just be a long number, but we didn't just use long for the user ID, we wrapped it in another type. By wrapping generic types like long into a more specific type, we gave the type some meaning. It's not just a number, it's a number that represents a user ID. We might have other numbers in our program, like a property ID, but the values of this user ID type are not that. This makes the code easier to read and helps to ensure the quality of our software. Imagine someone accidentally tried to pass a property ID to load user. If we just accepted a long there, our program would compile, and it wouldn't be until we tested it that we found out that it's broken. So we can take type safety a lot further than just proving that we aren't using a property ID where we expect a user ID. So Jack will now talk about some of the more advanced things that you can do in statically typed languages.
Thanks, Andrew. So Tim and Andrew have shown us how to use static types to improve the correctness of our code. There are other techniques that are more advanced, and I would like to show you a couple of them. So here is a line of code declaring a value called positive num to be -5. And it compiles and it works just fine. So this is quite upsetting to me. So we know the intention of the author is to create a number that is positive, right? So surely it is incorrect. So let's look at a technique called refinement types. So here, we've set the type of positive num to be a positive int instead of int. And positive int is a refined type, which is a type that has been refined with some sort of predicate. In this case, the predicate of, so the value needs to be greater than 0. Now, if we set the value to -5, we get a compilation error. Using this approach, we can refine a person's age to be between 0 and 110 and make sure that a person will never have an invalid age. In addition, we can refine the person's name to be a string that is not empty. So we can truly ensure that the objects we create are always correct upon construction. So languages that support refinement types often come with built-in refinements. For example, in Scala, there is a library called refined, which has one for refining URLs. So the top example has a URL with the wrong protocol. So we've set it to HTTP instead of HTTP. And what happens here is it fails at compile time, and we're forced to fix it without the need for tests. The bottom version has a valid URL with protocol HTTP, and it compiles. So this example is trivial, but the approach can be scaled to bigger problems, and we can truly make illegal states unrepresentable. So here's a familiar problem to us, hopefully. So this is a type signature of a function that appends two lists together, or at least it claims that it does. So it's written in a statically typed language. We can be certain that the input lists are a list of ints, and also that the output list is a list of ints. So off the bat, this eliminates a large category of errors. However, you could totally implement this simply by returning list 1 or list 2 without appending them together. Or you could just return an empty list. So that's not good, right? So how can we leverage the type system to prevent these mistakes? So let's have a look at a technique called dependent types. So first of all, this is not valid syntax in any language. So I've simplified the type signature so we can focus on the concept instead. So in this type signature, we can see that we're given two lists, a list of size n and a list of size m. And they both contain ints. The output is a list of size n plus m, also containing ints. So any implementation of this function that does not append the two lists together will not compile. You still have to write a test, of course, right? And you need to write a test to ensure that you're appending the lists in the correct order. But with types alone, we've eliminated a large category of errors, and we've also clearly communicated the intent of the function. So keep in mind that you can leverage a lot of what we've covered today in many languages. One of the most popular languages in the world, JavaScript, using Flow or TypeScript, supports ADTs. And there's actually work being done right now to bring in more advanced features, including refinement types. Thanks for listening. I'll invite the speakers back on stage for a Q&A, and I'll hand over Sanjiv to host our Q&A.
Thanks, everyone. Do you have any questions?
Oh, sorry. that was close. Yeah, is there such a thing as too much typing? Like, I'm sure you could go like right off the deep end with this and start doing like a custom type for every sort of ID in your application and stuff.
Yeah, I guess you can. Like in certain languages, I mean, just reading the types is like reading a whole program, right? You're like trying to figure out what the types do. But it depends on where your pain points are, where you're getting a lot of errors. And if you have a specific area that can be solved by adding those extra types, then I would try and do that. If there aren't many areas where you can like significantly get benefit by adding extra types, why would you do that? Like there's no use as an overhead. Yeah. But for certain cases, definitely I would add the types, but yeah, you can take it too far, definitely. But that also depends on the skill level of your team as well, as to what too far is, because certain teams have a better understanding of types than other teams.
Yeah, cool. Am I throwing this too? Oh.
Can I go first? Yeah, cool. So I know types can help us to avoid a lot of exceptions, but I still want to have a discussion about the last example, which is the sized list. I do think that might be a little bit over-designed because compared to a similar situation, if we want to append a set or union a set, yeah. So the functionality is quite similar, but obviously it cannot be sorted out by types. Still need test, but for list it doesn't need test. So might be a little bit confused for the developers. What things I need write test and what things I need to solve by types. So I think, do you have any best practices on define what levels of problem can be solved by types? Or
all right, I think Andrew kind of mentioned this. He said whatever you can easily solve with types, use types, yeah. And what you can't, use tests. So it sounds like for your use case, you don't want to write these types to prevent these errors. You'd rather write the tests. In that case, just write the tests. But by adding these types in, there's a class of tests you don't need to write at all. Right, and that might only work for lists, and maybe you don't care about lists, you only care about sets, and you can't use it. But if it's easy to use types, then use types. So others use tests.
Cool.
How can using types help improve security?
Obviously, using things like algebraic data types, ADTs, prevent invalid states in your code, so you only have your valid states coming into your code. So for example, like Tim mentioned, you can have something like an either representing your error states. Either it's valid as a right or invalid as a left. So you only handle valid states in your code, and those states are compile checked. So it ensures that you handle all the states. If you miss one, the compiler will say, hey, you missed this state, you need to handle this, right? So you don't have any invalid states if you encode them as ADTs, and you can easily handle them. And usually lots of the exploits come through these invalid states that are allowed through your program, and then something kind of uses that as an entry into your program. As an example, I think DARPA was using this to make a drone unhackable. So they had drones, and people were just hacking these drones and getting to do all sorts of different things. So they had some hackers to hack this drone. I think the drone software was written in Python. And then they got some people to use types to write proofs to verify that the drone could not be hacked, and they couldn't hack that. And so they realized that you can actually use some of these types to actually prove that certain things are not possible. And so that's like one of the military applications of kind of using really strong types.
In the case of in the examples of errors, and the case when you wouldn't find a user, why wouldn't you model this as a normal exception like you would find in Java and other languages like that, which is typed?
Yeah, so it depends how you can kind of use exceptions. And I think if you use Java like I have, you might say, I didn't have to find a user, so I'm going to throw an exception. That's an exceptional condition. But that's not really exceptional. You expect when you look for a user, it may not be there, right? So it's something that you expect. So you can encode that in like an ADT and say, okay, if the user's not there, I'm going to do this. I'm not going to blow the whole program up, right? And you can't kind of combine together or compose two things without throwing exceptions, because it becomes very hard, because you've got to handle exceptions at every stage along the way. And so by eliminating illegal states using ADTs, you can, by not using exceptions and using eithers or options, you can make that a lot easier.
I might just ask one more question on in a similar vein to the previous one. One of the things that happened in Java with in Java you declare your certain types of exceptions in the method signature to make it clear what your error cases are. And I think it felt to me like one of the reasons that started to struggle was that people became fatigued by declaring error behavior in all of their method signatures. I suppose my question is, why does that not apply to the use of either or try or future and the things that represent error case in method signatures in this kind of paradigm?
So in this case, within our program, we're defining what our valid states are. Whereas I think in Java, like every library that you use, if you threw a checked exception, then you'd have to handle every single different scenario that was thrown by each library and each method call. And you'd have this huge tree of exceptions that you need to handle that you actually didn't even care about, right? So you'd be just like try, catch, exception, ignore, right? Whereas in this case, we are saying within our program, these are the states that we care about, right? So we're not handling exceptions thrown. If you're using a library that throws an exception, we can wrap that and say, okay, if this library fails, this is the ADT we're going to use, and these are the states we're going to care about. We're not going to care about every single exception thrown by every single thing that we're using. We're going to convert that into something that we actually care about and only work on those. So you're restricting the number of invalid states coming into your system.
Yeah. And there are also techniques that allow you to work with, so if you have many eithers in your type signature, it might be really annoying for you to work with a function that gives you some kind of error 1 and the other function gives you error 2, and you might end up with 5 functions giving you different types of errors. So there are techniques that allow you to compose them differently, which we are not covering today.